In this video, I am going to discuss how to implement the Boolean functions using decoders. Decoder is a combinational circuit. It is a multiple output, multiple input logic circuit which converts coded inputs into coded outputs where the input and output codes are different. The input code has fewer bits than the output code. Then each input code word produces a different output code word. There is one-to-one mapping from input code words into output code words. Therefore, the decoder is a logic circuit which converts binary data in one coded form to another coded form. Here this is the block diagram representation of the decoder. We will represent n is to 2 power n decoder. From here itself we can see the input has less number of bits and the output has 2 power n number of bits. So the input has less number of bits compared to outputs. And these input lines are also called address lines. Then any one of the output lines will be enabled depends on the selection made in the address lines. And the enable inputs are optional one. Then here the encoded information is presented as n inputs producing 2 power n possible outputs, and the 2 power n output values are from 0 through 2 power n minus 1 values. Sometimes an n-bit binary code is truncated to represent fewer output values than 2 power n. For example, in the BCD code, the 4-bit combination 000 through 1001 represents the decimal digits, and the combinations 10 to 15 are not used. Generally, a decoder is provided with enable inputs to activate decoded output based on data inputs. When enable input is not active, all outputs of decoder are disabled. A decoder can be conveniently used to implement a given Boolean function. The decoder generates the required minterms and an external OR gate is used to produce the sum of minterms. In general, an n to 2 power n decoder and m external OR gates can be used to implement any combinational circuit with n inputs and m outputs. For active high output condition, the SOP functions are implemented. Now let's see how to implement. When the decoder output is active high, it generates minterms, that is product terms, for the input variables. It makes the selected output logic is 1. In such case, to implement SOP function, we have to take sum of selected product terms generated by the decoder. This can be implemented by ORing the selected decoded outputs. This is the logic diagram and block diagram representation for 3:8 encoder. So in this 3:8 encoder, 3 input lines. The inputs are 3 ABC and the enable lines are optional one. It will be active low or active high enable input. Then the outputs are Y0 to Y7. This is for active high output cases, and the output of each gate will be the minterms. The minterms are represented here. So this is the logic diagram representation and this is the block diagram representations. So here the minterms are available. So to implement the Boolean functions, we need to add the minterms. So to add the minterms, we have to connect the OR gate at the output of the decoders. Implement the function f of a comma b comma c is equal 1 to 3 7 for active high output conditions. So here we are drawing the 3:8 decoder and the three inputs ABC and outputs are Y0 to Y7. Each output we will get the min terms. So our outputs are 1, 2, 3, 7. So the min terms 1, 2, 3 and 7 is selected and it is connected to an OR gate. So the output at this position we will obtain is F. F is equal to 1, 2, 3 and 7 combinations. So this way we can easily implement the SOP functions for active high output conditions. Now let's see how POS functions are implemented for active high output case. Here the decoder output is active high. We can implement the POS function in similar manner as for POS SOP function, except the function output is complemented. So this can be achieved by connecting NOR gate instead of OR gate. This is the logic diagram representation for 3:8 decoder for active high output case. Here we are going to implement the POS expressions. So in this active high output decoders, the output we are obtaining is the min terms. So Y0 to Y7 we have 8 min terms. Min terms are available. Implement the following function for active high output conditions. So here we are using 3:8 decoder. The three inputs are ABC and the 8 outputs are Y0 to Y7. So the each output we are obtaining the min terms. So in our question 1357 is an output and we are going to implement the POS expressions here. So we are taken the outputs 1, 3, 5, 7 here, and for implementing the POS expression for our active high output conditions, we have to use NOR gate instead of OR gate. So we are using NOR gate here. So the expression at this position is this one, A bar B bar C plus A bar B C plus A B bar C plus ABC, the whole complements. Then we are applying the De Morgan's theorem here, break the lines and change the sign. So addition sign is changed to multiplication and the lines are broken. Then again we are using the De Morgan's rules here, break the lines and change the sign. So now our expressions are obtained in max terms. So the A double complement value is equal to A, that is A double bar is equal to A, B double bar is equal to B. So now we are writing the equivalent binary values. After that we are writing the equivalent decimal values. The decimal value we obtained is 1357. So the expressions what we are implementing here is F is equal to 1357. Now let's see how we can implement the POS function for active low output conditions. When the decoder output is active low, the output is in complemented form. It generates max terms for input variables. So it makes selected output logic is 0. In such case, to implement POS function, we have to take product of selected sum terms generated by decoder. This can be achieved by handing the selected decoded outputs. For implementing the active low outputs, we have to use the active low logic diagram for implementing the POS functions. So this is the active low logic diagram for 3:8 and decoder. So the outputs we will obtain each point is Y0 is equal to A plus B plus C and Y7 is equal to A bar plus B bar plus C bar. That means we are obtaining Y0 to Y7 outputs or in max terms. So this is we can represent in block diagram is in complemented form. So that is a NAND gate we are using here. Outputs are in max terms. So the block diagram representation for 3:8 decoder is like this. So here the outputs are represented as complemented term and we are obtaining the max term at the output side. Implement the following Boolean function for active low output conditions. So this is a 3 variable output. So we are using 3:8 decoder. The inputs are A, B, C, and the enable input is optional one. And the outputs are Y0 to Y7. It with the NAND gate is used here. So we will obtain the max terms at the output. So now POS expressions are represented as like this, the product of max terms. These are the product of max terms. So already we are obtained max terms here. Each gate we are getting the max terms. So to obtain this expression, just we need an AND gate. So we are connected the AND gate here. So the outputs are 1, 3, 5, 7. We are connected to the AND gate. So the expression we will obtain this point is F. Now let's see how we can implement the SOP function for active low output conditions. So when the decoder output is active low, we can implement the SOP function in similar manner as for POS function, except the function output is complemented. So this can be achieved by connecting NAND gate instead of AND gate. Implement the following SOP function for active low output conditions. So the active low output conditions we are using then decoder with the active low output combinations. So the output at each point we are obtained is a max terms. So the inputs are 3, it's represented here, and the outputs are Y0 to Y7. Each output we are obtaining the max terms. So for our questions we have 1 to 5, 7 as an output. So we are selecting 1, 2, 5, 7 max terms and we are connecting to one NAND gates here. Then we will see how we can obtain SOP expression at this positions. So the expression at this position is F is equal to A plus B plus C bar, A plus B bar C plus A bar plus B plus C bar plus A bar plus B bar plus C bar. Here NAND gate is used, so we are complemented the whole max terms. So after now we are simplifying by using normal De Morgan's theorem. So break the lines and change the sign here. So we are breaking the lines. So the multiplication sign changed to plus sign. Then again we are applying the De Morgan's rules here. Break the lines and change the signs. So we will obtain min terms here. So now we are writing the equivalent binary values. So then again we are writing the equivalent decimal values. The decimal values are 1 to 5, 7. This is the SOP expression representation. So we will obtain 1 to 5, 7 at the output of NAND gates. Implement the following multiple output function F1 and F2 for active low output conditions. F1 is in SOP term and F2 is in POS term for active low output conditions. So here we are taken active low output decoder. 3:8 decoder is chosen and the inputs are ABC, and these are the enable inputs G to GB, and this is the ground sorry, this is a supply of an decoder IC. Now the max terms we are obtained from the decoder output. So here for SOP function implementation we need to use NAND gate, and POS function implementation we need to use an AND gate. So this way we can implement any multiple output function. Implement the following function 1356 that it's in SOP form. So for active high output implementation conditions we are using the decoder with the max term at the output. So we are connected an OR gate to get the output. So this way we can implement the functions. Implement the full adder circuit using 3:8 decoder. Full adder have 3 inputs, so we can use 3:8 decoder. The outputs are sum and carry. Here this is the truth table for full adder. We are adding A plus B plus C. So for first 0, 0, 1 condition sum is 1, carry is 0. 0, 1, 0 condition sum is 1, carry is 0. 0 1 1 condition sum is 0 carry is 1, and 1 0 0 condition sum is 1 carry 0, 1 0 1 condition sum is 0 carry 1, 1 1 0 condition sum is 0 carry is 1, 1 1 1 condition sum is 1 and carry is 1. So from this we are taking the logical the SOP expressions for sum and carry. For sum the logical expressions are 1 2 4 and 7, and the carry outputs are 3 5 6 and 7. So it's represented here. Now we are going to implement in the decoder for active high output conditions. So the sum and carry expressions are there, and the 3 to 8 decoder is represented, and the selection lines are A, B, C. And here the outputs are 0 to 7 is represented, and it's for active high output. So min terms is available at each output of the decoder, and so we are connecting OR gate at the outputs. The sum output is 1 2 4 7 and the carry output is 3 5 6 7. It's connected based on the input conditions. Now we are going to implement the full adder for active low output conditions. The active low output conditions, the output we are obtaining as max terms. So the Y0 to Y7 max terms are available, and the 3 inputs lines A, B, C. So max term conditions, we have to use NAND gates and AND gates. Here we are using the SOP expressions for sum and carry. So we are using the NAND gate. So this is the NAND gate for carry expression, and this is the NAND gates for sum expression. Now we are going to implement the full subtractor using 3:8 decoder. The full subtractor have 3 inputs that's represented as A, B, C, and the outputs are borrow and difference. So for the first input 0 0 0, borrow difference, borrow and difference is 0 0. For 0 0 1 condition, borrow 1, difference 1. 0 1 0 condition, borrow 1, difference 1. 0 1 1 condition, borrow 1, difference 0. 1 0 0 condition, borrow 0, difference 1. 1 0 1 condition, borrow 0, difference 0. 1 1 0 condition, borrow 0, difference 0. 1 1 1 condition, borrow 1, difference 1. From this our SOP terms are for borrow 1 2 4 and the borrow is 1 2 3 and 7. The difference is 1 2 4 and 7. This is written here. Now we are going to implement the full subtractor for active low output conditions. The difference and borrow expressions are given. For active low output conditions, we are using a NAND gate decoder. So the each output of the decoder we obtained as the max term. So max term expression is obtained from Y0 to Y7. Now for active low output conditions, to implement the SOP expressions, we need to use a NAND gates. So the NAND gates are connected here, 2 NAND gates. One is for difference and another is for borrow, and the corresponding min terms are connected to the NAND gates. So for difference 1 2 4 and 7, it's connected to difference, and for borrow 1 2 3 and 7 is selected and it's applied to another NAND gates. This way we can implement the full subtractor. Now we are going to implement the following logical expression Y by using 3:8 decoder. Here from the expression we can see it's a 3 variable input. So we are selecting 3:8 decoder, and the outputs are represented as an expression. These expressions are in sum of min terms. So the min terms we are obtaining from this point. 1 0 0 for this one is 4. So fourth output is selected, and here this is 0 1 0. That means 2 is selected. This is 1 1 1. That is 7 is selected. This is 0 0 0. The input 0 is selected. These selected inputs are given to an OR gate. Design the 2-bit magnitude comparator using decoder. The 2 input bits are A and B. So A is represented as A1 A0 and B is represented as B1 B0, and outputs are A greater than B, A equal to B, and A less than B. So this is the output output table of the magnitude comparator. From this table, we are going to take the SOP terms. Now from the truth table, we are getting the SOP expressions for A greater than B, A equal to B and A less than B. This is the decoder implementation circuit for a 2-bit magnitude comparator. The 15 D0 to D15 total 16 outputs are represented here and the 4 inputs are represented here. Now the outputs are A greater than B, A equal to B and A less than B. These decoder outputs are connected to each OR gates based on the SOP expressions. So this is the implementation diagram for 2-bit magnitude comparator using decoder. Design a 3 to 8 line decoder with the use of a 2 to 4 line decoder. So here we need 2 to 4 line decoder. The first decoder, the outputs are Q0 to Q3 and the second decoder outputs are Q4 to Q7. And so total 8 outputs are obtained like this way. Now the inputs are 3. The 3 inputs are X, Y and Z. Here one of the input is act as an enable input. So X is connected to the decoder 2 directly and X is connected to the decoder 1 through the inverter. So now we are writing the 3 input combinations here. So the first 4 combinations, the X is 0. In this case, decoder 1 is activated because we are applying the X input through the inverter. So when X is equal to 0, here this point will become 1. So the decoder 1 is activated. At the same time, decoder 2 is deactivated. Next, the D4 to D7 combination, X is equal to 1. This condition, decoder 2 is activated and decoder 1 is deactivated. So when X is equal to 1, we will obtain 0 output. So decoder 1 is deactivated and X is equal to 1. This condition, decoder 2 is activated. So based on these conditions, the decoder is working. Design a 4 to 16 line decoder with 2 3 to 8 line decoders having active low enable inputs. Here 2 3 to 8 decoder is used, decoder 1 and 2. Decoder 1 have output as D0 to D7 and decoder 2 have output as D8 to D15 and the 4 inputs are A, B, C, D. One of the input is act as an enable input. Here D is act as an enable input. So active low enable input means whenever the enable input is 0, the decoder is activated. So here when D is equal to 0, decoder 1 is activated and D is equal to 1, decoder 2 is activated. So this is the truth table. Here D0 to D7 conditions, the D value is 0. So decoder 1 is activated at this position. And here D8 to D15 combinations, D value is 1. Here decoder 2 is activated. Design 5 to 32 decoder using 1 2 to 4 decoder and this is 1 2 to 4 decoder and 4 3 to 8 decoders. The input is 5, so the 2 power 5 is equal to 32 combinations. The total outputs are 0 to 32. So decoder 1 have the output is 0 to 7 and the next decoder have the output is 8 to 15. The third decoder has the output is 16 to 23 and the fourth decoder have the output as 24 to 31. Then here the outputs are represented here. For this case, the inputs are A, B, C, D and E. So here we can represent as 0002 1111, and this is the enable input. Now the DE is act as a selection inputs. So when 00 combination Y naught is activated, that means the decoder 1 is activated. Next 01 combination of input Y1 is activated, decoder 2 is activated here. Next 1-0 combination Y2 is activated, means third decoder is activated. Then 1-1 combination Y3 output is activated, that means fourth decoder is activated. This Y0 to Y3 act as an enable input for each decoder, and this A, B, C, these are the three input for each decoders, and these D and E inputs are act as an selection inputs. So for Y naught combinations, the DE inputs are 00. So here you see that D naught to D7, the DE inputs are 00 up to this combination. Next Y1 output combination, DE is 01. Here you see D8 to D15 combination, DE value being 01. Next Y2 combination output, DE value is 10. So here D16 to D23, the DE value is 10. Next 1-1 combination, Y3 is selected. Here the DE value is 11. D24 to D31 is represented as DE values are 11. So this way we can implement the 5 to 30. Design 4:16 decoder using 2:4 decoder. Here the inputs are 4, that is A, B, C, D, and the outputs are 16, D0 to D15. Here we are using total 5 2:4 decoders. The 2:4 decoder is act as an selection decoder. This decoder will select which decoder has to connect to the output side. So decoder 2 outputs are D0 to D3, decoder 3 output is D4 to D7, decoder 4 output is D8 to D11, and decoder 5 output is D12 to D14. D15. Now the CD is one of the inputs. This is applied to all the decoders, and here AB is another input. This first decoder output is act as an enable input for each decoders. So when AB is 00 combination, D0 is selected. So D0 is connected to decoder 2. So in this case AB value is 00. So now AB is 00, D0 is selected, it will enable decoder 2. So this condition we will get the output as D0 to D3. Here our input values AB are 00. Next 01, AB is 01, D1 output is selected. So this will enable decoder 3. So we will obtain the outputs are D4 to D7. This condition, our AB value is 01. So we will obtain the output value is D4 to D7. Next AB is 10 combination, D2 is selected, so it will enable the decoder 4. So we will obtain the outputs are D8 to D11. In this case our AB values are 10, 1 for D8 to D12 combinations. Next AB is 11, D3 is selected, it will enable decoder 5. So we will get the outputs are D12 to D15. In this D12 to D15 our AB values are 1, 1. This way we can implement 4:16 decoder. Design a 3-to-1 multiplexer using 8-to-1 multiplexers having an active low enable input and a 2-to-4 decoder. And so the 2-to-4 decoder is used to select the multiplexers. So here 2 to 4 decoder, the inputs are S4, S3, and the S0, S1, S2 is selection lines. This selection line is common for all the 481 multiplexers, and finally all the multiplexer output is connected to an OR gate. So here first, this decoder will decide which multiplexer has to selected to the output. So for when S3, S4 is 0, 0, output will be Y0. So the Y0 is connected to multiplexer 1. So the multiplexer 1 is selected. Next 0, 1 combination, the output will be Y1. So the second multiplexer is selected. For 1, 0 combination, the output is Y2. So the third multiplexer is selected. Next 1, 1 combination, the output is Y3. So the fourth multiplexer is selected. So like this we can design 32 to 1 multiplexer. Thank you.